Namaste, welcome to Pythagoras Academy. This is Vikram Dachepally. In this video, I'll discuss a very good technique to deal with wedge constraints. Now consider this wedge whose angular of inclination is theta, and it has got some acceleration a1 towards right and the other block m2 which is restricted to move only in the vertical direction. So it is accelerating down with an acceleration a2. I want to find the relation between a1 and a2 because m1 and m2 are in contact, and as long as m1 and m2 are in contact, their motion is constrained by each other. So what is the relation between a1 and a2? So in general, without applying any technique, if you have to analyze this case, it is like this. Say after some time, so consider some time has elapsed and the wedge has moved by a small distance x. So now the block m2 has got a vertical displacement of y. So this is y and this part, this is x, the horizontal displacement. So consider this point on the wedge. Initially it was here, now it moved by x distance because the displacement of the wedge is x, the displacement of the block is y downwards, and if this angle is theta, so this is also theta. Alternate angles are equal. Now the relation between y and x is tan theta, that is equal to y by x, or y is equal to x tan theta. So if you differentiate this dy by dt, that is equal to dx by dt, which is v1 velocity of the wedge m1 into tan theta. If you differentiate this, because theta is constant, dv2 by dt, that is a2, which is equal to dv1 by dt, that is a1 times tan theta. This is method 1. So there is a shortcut to deal with the same problem. So this is the relation between x and y. Differentiating and double differentiating, we can get the relation between a1 and a2. Method 2, another simple method. The logic what we are applying is, if two surfaces are in contact, say there are two surfaces in contact, say a block is placed on the ground, or there are two blocks one on the other. If two surfaces are in contact, the surfaces can slide on each other, but the components of these two surfaces perpendicular to the surfaces of contact should be same. Say this is the surface 1 of the block, this is surface 2 of the ground. So perpendicular to the surfaces, so if the velocity is v1 of the surface and the other surface has got velocity v2, then v1 must be equal to v2. The simple logic is this. Only if v1 is equal to v2, they are in contact with each other. If v2 is more than v1, or if v1 is more than v2, so there is, if v2 is more than v1, then there is no more contact between 1 and 2. So they get separated. If the velocity of this surface on which this block is placed is more than the velocity of the surface of the block, then definitely they get separated. There is no more contact observed between two surfaces, block surface and the platform surface. If velocity of the block surface is more than the platform surface, then one is going into the other. So the block will go into the platform, it will break the platform and go into it. So neither the surfaces are getting separated from each other, nor the surfaces are going into each other. If they are just remaining in contact with each other, then the components of their velocities along the perpendicular to surface, along the normal, should be equal. So v1 is equal to v2. I am going to apply the same concept here. If you observe the inclined plane or the wedge, so this is the wedge surface, I will represent with a dotted line. This is the wedge surface. This is actually making an angle theta with x-axis or with the horizontal. Now this wedge surface is accelerating towards right with A1, and the other surface is accelerating down with A2. Now normal to the surfaces in contact is this. So I am representing with a yellow dashed line like this. So the components of accelerations of two surfaces along the normal to the contact must be same because they are in contact. Applying this logic with just one step, we can arrive at the same result. So if this is theta, 90 minus theta, so this angle is theta. So this would be 90 minus theta. So the component of A2 along this yellow dashed line or along the normal to the surface in contact is A2 cos theta. The component of A1 along this normal to the surface in contact is A1 cos 90 minus theta. Both must be equal. Only then, so this is the normal to the surfaces. Only then those two surfaces are not getting separated from each other, nor they are getting into each other. They are just remaining in contact. So in that case, so this is one step equation. So A2 cos theta is equal to A1 cos 90 minus theta, that is sin theta. So take cos theta on the other side. A2 is equal to A1 tan theta. As simple as this. I can take another example for applying the same wedge constraints equation. Yeah. Say there are two blocks as shown in the figure, M1 and M2. Suppose the velocity of M1 is 10 meter per second towards right. The question is to find the velocity of block M2. What is this V2? So in this case, again, you can apply the wedge constraints. So I'll represent the surface with the surfaces in contact with the dashed line, this one. This is making an angle 37 with horizontal. M1, so this is V1. M1 is moving with a velocity V1. So it is making angle 37 with this dashed line. Anyways, I need the component of these velocities V1 and V2 along the perpendicular to this surface. So this is the perpendicular, this is the normal to the surface. Along this normal, both the blocks should have same components. Only then they are in contact with each other, right? So you can resolve this V1, so this is 37, so this would be 53. So the component of V1 along the normal is V1 cos 53. Similarly, what about V2? So V2 is vertical, along the vertical, so it is going up. Now 53, so this would be angle 37. So the component of V2 along the normal to the surfaces in contact, along this white dashed line, is nothing but V2 cos 37. So the equation is simple. V2 cos 37 is equal to V1 cos 53 or sin 37, anything is fine. Cos 90 minus 37, I can write it as sin 37. So V2 into the value of cos 37 is 4 by 5, which is equal to V1 into the value of cos 53, which is sin 37, that is 3 by 5. So 5 is gone. V2 is 3/4 of V1, that is 3/4 of 10. So V2 is equal to, so 2 5s, 2 2s, so it is 15 by 2, which is 7.5 meter per second in the upward direction, obviously. So obviously if the block M1 is moving towards right, M2 will have velocity in the upward direction. So this is how we apply the wedge constraints. Let us take another simple example. So this is a different kind of question where there's a wedge, movable wedge, which is moving towards left with a velocity of 20 meter per second. You are supposed to find the velocity of the block relative to wedge. This is the important part of the question. You are supposed to find velocity of the block relative to the wedge. So in that case, I can apply a simple constraint equation. So I'll take this as x and I'll take this as y. So dx by dt, the rate at which x changes with time, is nothing but velocity of the wedge m1. Whereas the rate at which the y changes with time, dy by dt, is simply v, that is velocity of m2 relative to the wedge. Now if you observe this, the string length x plus y is constant. It's a very, very simple equation. So I can differentiate this dx by dt plus dy by dt is equal to 0. So dx by dt is given to be 20. So I'll take the direction of velocity, which is in the direction of decreasing distance, as negative. If the direction of velocity is in the increasing distance, then I'll take it as positive. In this case, if the wedge is moving towards left, x is actually decreasing. So dx by dt, I'll take it as negative. So I'll put a minus 20 sign. Plus, if v is downwards, then definitely y is increasing. So dy by dt is v, which is plus v because it is in the direction of increasing y. So let plus y, that is equal to 0. So y is equal to 20 meter per second. Sorry, this is not y, this is v. So v is 0. So v is equal to 20 meter per second. dy by dt, that is v. That's all. The velocity of the block relative to the wedge is simple, 20 meter per second. You don't even have to do this in this question, because if wedge moves towards left by 1 meter, suppose the wedge is here, 1 meter of string is released and 1 meter is given to m2 with respect to the wedge. So if the velocity of the wedge is v towards left, then velocity of the block with respect to the wedge will be v downwards. So in that way we get velocity of the block with respect to wedge as 20 meter per second. If the question is find the velocity of the block with respect to ground, so then I can use this velocity of the block with respect to wedge is velocity of the block minus velocity of the wedge. So velocity of the block as seen from the ground is velocity of the block with respect to wedge plus velocity of the wedge. So we just have to add these two vectors. So we have v in this direction. So this is 30, so this is also 30. So v is in this direction and velocity of the wedge is in this direction, 20 meter per second. So the resultant of these two, so some direction. So this is velocity of the block as seen from the ground. You just have to add these two vectors properly. So you can resolve v and express v in terms of I and j, and velocity of the wedge is minus 20 I cap. Just simply add both of them, you would get velocity of the block as seen from the ground. So these are different cases of wedge systems, and very easily you can find the constraint equation as far as the wedges are concerned. That's all. If you have any questions or queries or suggestions, you can always use the comment section to interact with me. I'll be more than happy to respond and receive your feedback. This is Vikram Dachepally signing off. Namaste.